Hello and welcome. In this video, I'm going to talk about some very basic concepts of fluid mechanics. Let's start with defining what a fluid is. Now, generally speaking, a fluid is a substance that deforms continuously under the application of shear stress, no matter how small the shear stress may be. Now, let me show that with a drawing here. So let's say this is a element of a solid, and this is another element, this time of a fluid. I'm going to apply the same shear stress on both of these two elements. So what's going to happen is that for the solid, obviously under the effects of this shear stress, we will experience some sort of a deformation, right? So the solid element maybe changes to this red shape. Now the thing is, after the deformation is done, the solid stops deforming any further and is just stays like that. As long as the tau, the shear stress that we're applying on the solid is smaller than the yield stress, the solid will not deform any further. However, for the fluid, that's not the case. Under any shear stress, no matter the magnitude of the stress, the deformation continues. What I mean by that is that after maybe a time interval of delta t, fluid element also deforms to this red element, right? After time passes about 2 delta t, deformation continues to this green. And let's say after time has passed 3 delta t, the deformation keeps continuing the orange one. So as you can see, the deformation continues under the effects of the shear stress, while for the solid, the deformation stops. So this is the main difference between a solid and a fluid. Fluid keeps deforming under shear stress, while solid does not. For this reason, solids are usually called elastic, while fluids are usually called viscous. Another major difference between solids and fluids is the way that we treat them with different equations and concepts. For example, a very famous equation that governs the balance of forces on any object is the Newton's second law. We know by definition that sum of all forces in the vector form is equal to the mass of the object times the acceleration vector. Now, applying this equation on a solid is relatively straightforward. And that is what we do in subjects like dynamics and the design of machineries and stuff like that. However, applying this equation in this form on fluid particles is actually impossible. If you think about it, when you have a flow, let's say inside a pipe, there are numerous fluid particles moving through this pipe. So if you want to apply this Newton's second law on each of these individual particles, you will end up with a very complex system of equations. In order to bypass this issue, we are going to change the way we apply this equation in fluid mechanics. Instead of following each particle individually using the Newton's second law, we are going to set aside a defined geometry in space, like this green rectangle that I'm drawing here. We call this control volume. We are not concerned with the motion of the individual particles. We are concerned with the motion of the flow inside the green rectangle. So this is a new approach. The other approach, following individual particles, the motion of individual particles, the approach that is generally used in solid mechanics, is usually referred to as the Lagrangian approach. A new approach for fluid mechanics, where we are really concerned about the motion inside a defined geometry in space, is usually referred to as Eulerian approach. We are going to discuss the Eulerian approach in future videos. For now, I just wanted to introduce the concept and the difference between Lagrangian and Eulerian approaches. Now, in a control volume, generally speaking, if this is our control volume, flow and fluid properties can be different at different locations inside our control volume. For example, at this location, let's call it point A, we will have the density of point A, velocity of point A, temperature of point A, and pressure of point A. And at another point in the same control volume, let's call it point B, we may have density, velocity, temperature, and pressure that are different at point A. So generally speaking, the flow properties can be a function of location as well as time. So for example, the density of the fluid is a function of x, y, z, and time. X, y, z here represent the 3 dimensions in the 3D space for a Cartesian coordinate system. If you are, for example, using a cylindrical coordinate system, then the functionality will be density is the function of r, theta, and z, as well as time. As I said, this is for a rectangular coordinate system, and this is for cylindrical coordinate system. Now that I mentioned density, let's talk about it. Density is defined as mass per volume. The unit for density in SI units is kilogram per meters cube. In British Imperial units, it is pounds per cubic feet. There is a traditional way of representing density of different fluids and materials in general, and that is showing the density based on the density of water. It is called the specific gravity, and we show it with Sg. It is the ratio of the density of the material that we are talking about over the density of water. So, for example, Sg of mercury is 13.6. What it means is that density of mercury over density of water is 13.6. And now, in standard conditions, room temperature and pressure of 1 atmosphere, the density of water is 1,000 kilograms per meters cube. That means density of mercury is 13,600 kilograms per meters cube. That's how you use specific gravity. Now, after density, the other flow property that is very important is the velocity. So we need to define the velocity field. Now again, just like density, velocity in general is a function of x, y, z, and time. Now, please take note that unlike density, that was a scalar, velocity is a vector. Now, when dealing with vectors, it is immediately known that we can write down the vector in its component form. So, for a rectangular coordinate system, I can write down the velocity vector in the form of its I, j, and k components. So I will have u, I, plus small letter v, j, plus small letter w, k. Now I, j, and k in this equation represent the unit vectors along x, y, and z axis. And small letter u, small letter v, and small letter w represent components of the velocity in x, y, and z directions. Now, using u for the velocity component in x direction, v in y direction, and w in z direction is kind of like a general universal agreement in all of the fluid mechanics textbooks. So everywhere you go, when you see u, you can be certain that u is along the x-axis. Small letter v is always the velocity component along the y-axis, and w is the velocity component in the z direction. Now, based on the number of space coordinates required to specify the velocity field, a flow is classified as 1, 2, or 3-dimensional. Now, generally speaking, all flows are 3D, right? But analysis based on fewer dimensions is always appreciated, okay? So let's take a look at the flow inside a pipe. Now, again, we are going to derive this equation that I'm going to use for the flow inside the pipe in future videos. But for now, just accept that this equation is governing the velocity inside the pipe. Now, the velocity profile inside this pipe looks like this profile that I just drew. Now, if we are using the cylindrical coordinate system and this direction is the r direction and the radius of the pipe is capital letter R, then the velocity is defined as capital letter U times 1 minus small letter over capital letter R squared. Now, in this equation, the capital letter U is just a constant. Capital letter R is the radius of the pipe, so it's constant as well. The only variable here is small letter r. So I can conclude that U is a function of r only. So my velocity component, my velocity profile, has only one space coordinate. I only need one space coordinate, r, to define the velocity field. This means that this flow field is one-dimensional. Now let's assume another situation where we are dealing with a pipe. However, the cross-section of the pipe is shrinking. More like a cone. So the velocity profile at the beginning of this cone looks like this. And the velocity profile at near the end of the cone looks like this. As you can see, the velocity profile has changed in the x direction as well as r direction. Again, we are using the cylindrical coordinate system. This direction is r, this direction is x. I can see that u is a function of r, obviously, as you move in the r direction from the center line to the edges of this pipe, the velocity profile changes. So it's a function of r. And also, it is a function of x as well, because it is kind of obvious here. At the entrance of this cone, the velocity profile is kind of broad and wide. And as you go closer near the tip of the cone, the velocity profile is shrinking. So velocity field is a function of x as well. So this means that this flow is two-dimensional. Now take note that in these two examples, we are dealing with a velocity field that has only one velocity component, namely the velocity in the x direction. That's why we call it u. We are not dealing with v or w. Okay, these flows do not have v or w components. However, especially for the bottom example, because that single velocity component is a function of r and x, At the same time, it is a two-dimensional flow, despite the fact that only one velocity component is present. So when trying to define the dimension of a velocity field, don't concentrate on the number of velocity components, concentrate on the number of space coordinates that are required to define your velocity field. Now, we talked about the dependency on space coordinates, but what about the dependency on time? Now, as it was mentioned for the definition of density and the velocity, both of these are, generally speaking, functions of space coordinates as well as time. Now, again, in general, every flow property, I'm just going to use x here, just to show that x can be any property, any flow property. Any flow property is a function of x, y, z, and time, generally speaking. Now, if the flow properties are not changing with time, or in other words, mathematically speaking, the derivative of the flow property with respect to time is 0, then I can conclude that the flow is independent of time, or in other words, is steady. If, however, the flow properties are changing with time, we can conclude that the flow is unsteady, sometimes referred to as transient. The dependency on time and spatial coordinates are independent from each other. We can have a scenario where velocity is a function of x and time. We can have a scenario where velocity is a function of time only, or a scenario where velocity is a function of spatial coordinates alone and not time. So there is no correlation between the dependency on time and spatial coordinates. Okay, they are independent from each other. There are independent variables, and they don't affect each other. So in the previous example that we had, the flow in the pipe, I presented this equation as the velocity inside the pipe, right? Now, as you can see, there is no time involved in this function. Obviously, you can conclude that the velocity inside the pipe governed by this equation is a steady flow, meaning that flow properties are not affected by time. Now we can talk about our next topic, path lines, streak lines, and streamlines. Now, path line is the trajectory or path of a single moving fluid particle. If we follow all the particles that pass through a fixed location over a certain time frame, and then we connect these together, then the line that we get is called a streak line. And finally, streamline is a tangent line to the direction of the flow at every point in the flow field at any given time. Now, the video here shows path line, streak line, and a streamline at the same time. This is a transient flow. We can think of it as the wind blowing initially towards the east, or the right-hand side of the x-axis, and over time, it gradually shifts its direction towards the north. So at the end of this animation, the wind, or the direction of the wind, is towards northeast. Okay? Now imagine that at the center of this coordinate system, we have a pile of particles. Think of them as maybe 3 leaves that are on the street. we are going to gradually release these particles into the flow. And we have attached a GPS to each of these particles so that we can track them in the wind. So the red line here is the path of a single particle or a tree leaf. It initially starts to move towards the right, and gradually as the wind shifts direction, it also shifts direction towards the north. And as you can see, it goes through a curvature. So the red line is a path line because it's following a single leaf. Now, we are gradually releasing all the leaves into this wind. And at any given time during this video, if we pause and connect the GPS of all these particles together, we get the blue line. So the blue line here is the streak line. It shows the location of all the particles that originated from the center of this coordinate system inside this flow field. As you can see, the blue line is not following the red line because generally speaking, streak lines and path lines are not the same. Finally, the gray dashed lines in this video represent the streamlines. They are always tangent to the direction of the velocity of the flow. And again, this is a transient flow. They are initially all parallel with the x direction, with the x-axis, meaning that the flow is going towards the right, or the wind is blowing towards east. And over time, they start to shift direction towards northeast. At any given time, these dashed lines show you the tangent lines or the streamlines inside our velocity field. Now, this was an example of a transient flow. In a transient flow, generally speaking, path lines, streak line, and streamlines are different. For steady state flow, on the other hand, this is not the case. In a steady flow, path line, streak line, and a streamline are the same. Because if the flow is steady and there is no change with time, a single particle that originates from any point in space will go through the same path as any other particle that have originated from the same location in space. There is no change with respect to time, so all the particles will follow each other. So all the particles will go through the same path line. If you connect them at any given time, the streak line will also fall on the path line. And because they are following that path line at any time, this is a steady flow, so it's not dependent on time. So streamlines also fall on the path line. So all three are the same. So to summarize, in a steady flow, path line, streak line, and streamline are the same. In an unsteady flow, they are different. So by the definition of a streamline, we are looking for a tangent line that is always tangent to the direction of the flow in a velocity field, right? So let's see what we can do with that definition. So let's say we have a flow field, and at a point inside my velocity field, I have this velocity vector, right? Now let's see if we can find a tangent line to this vector. Let's say this is the line that we are looking for, right? I want to find a mathematical equation for this green line. I'm also using the rectangular coordinate system x and y. So basically what I want to do is find the slope of this green vector. So I have two ways of achieving that. First, I can break this vector into its components, u and v. Finding the slope means finding this angle here. Let's call it alpha. So tangent of alpha is v over u. Now, if you take a look at the green line and I ask you, okay, if this green line has a function of y is equal to y of x, now tell me what the slope is at this blue point, what would you do? You would say that the tangent alpha, or the slope there, is dy over dx, right? Now I have two definitions for tangent of the same angle. I can equate them. dy over dx is v over u. I can play with this equation and say dy over v is equal to dx over u. Okay? This equation relates the velocity components u and v to the streamline. Now this is in two-dimensional. In three-dimensional, we don't have a streamline, we have a stream tube. And we can expand this green equation to include the third dimension as well. So for the case of three-dimensional flow, we have dx over u is equal to dy over v, which is equal to dz over w. So this is the equation for the stream tube. The green equation is the equation that we use to find the streamline. Okay, so basically, generally speaking, if you have the velocity components u and v, then you can derive a differential equation for your streamline. This is the equation that most of the softwares, the CFD softwares, post-processing CFD softwares to be more precise, use to generate the streamlines in the solution domain. We can do a little mathematical analysis for the path line as well. Now, path line, by definition, was the trajectory of a single particle, right? So I can say, okay, the velocity of the single particle has two components, u and v. We're talking two dimensions here. So u and v. Now, by definition, u is the derivative of x with respect to time, and v is the derivative of y with respect to time, right? So playing with both of these equations, I can actually say that x as a general function of time, I'm talking about the x of the particle. This is a Lagrangian approach because we are following a single particle now. X as a function of time is the integral of u dt from the start of the motion up to t star, which is the time that we are interested in. Same thing goes for y. Y as a function of t is the integral from the initial time to t star, the time that we're interested in, of v dt. Now again, finding the path line, these equations, these two integral equations, are the ones that we generally use to find a path line of a single particle. And again, these are the equations that these CFD softwares, post-processing CFD softwares like TechPlot, usually use to generate a path line. Now, streak line, on the other hand, is, because of its definition, is very easy to visualize using a wind tunnel and using smoke or dye and injecting some dye into the fluid. And as I said, it's very easy to visualize. However, it's more tricky to actually find an equation analytically. So I'm not even trying to do that right now. Path line and streamline in equation form are enough for now. All right, so now we can talk about the stress field. Now, when analyzing a fluid flow, we really need to know the different forces that are acting on our fluid. Now, generally speaking, the forces acting on a fluid element or a fluid particle can be categorized into two main groups: surface forces and body forces. Now, body forces are the ones that affect the bulk or the mass or the volume of a particle, like gravity. Or, for example, if your fluid has electromagnetic properties, then applying an electric or a magnetic field on the flow will generate or cause some sort of body forces. right? So gravity and electromagnetic forces. Now keep in mind that in classic fluid mechanics, the ones that we usually encounter in general engineering applications, we are usually dealing with the gravity. Electromagnetic is rare, but it depends on your problem. If your flow has electromagnetic properties and there is an electric or a magnetic field present, you have to consider that. Now, anything other than body forces fall into the surface forces category. Things like pressure or friction. Any other type of force imaginable that is not a body force is categorized as a surface force. So surface forces lead to stress. This part is just like the solid mechanics. When you have a solid element, a solid particle, and you apply different surface forces on it, depending on the direction of the force, it causes either a normal stress or a shear stress. The same thing happens here in the fluid mechanics as well. So let's take a look at it. So let's say this is the surface of a fluid or a solid particle, and we are interested in this blue element here. I'm going to call this blue element S. This is just an area. Okay. Now, area, generally speaking, is a vector. So I'm going to show S as a vector. It has a unit vector. I'm going to show it with N, meaning that it's normal to the surface that we are interested in. The area's unit vector is always perpendicular to the surface of interest, and it's always pointing outward of the element. So, for example, if this green surface that we are discussing here is on top of the element, is on top of the fluid particle that we are talking about, then the orange N is pointing outward. Okay? Now, there is an orthogonal vector in the direction of the surface itself. We show that with T. So based on this vector representation here, I can say that vector S is Sn, where S here is the scalar number representing the magnitude of the area, and N represents the normal vector of the surface. A general surface force vector can be something like this. Let's say this is the force, surface force acting on my element S. I can break this force into N and T components, right? So let's do it. So this will be the component in N direction, and this will be the component in T direction. Now, based on the definition of normal and shear stress, I can say, okay, normal stress, we usually show it with a Greek letter sigma, small letter sigma, in N direction is Fn over S, the magnitude of the area. And then I can say, okay, the shear stress, we show it with Greek letter tau. It's in T direction, obviously, and it will be the force component in the T direction over the area S. Now, N and T vectors here are not good enough for us. Let's take this analysis and put it onto an element that exists in a rectangular coordinate system. This is my X, Y, and Z coordinate system, right? Now I'm talking about this green element, which in this case is parallel to ZY plane, and so the x-axis is perpendicular to its surface. Just like the analysis of the last page, I know that there is a normal stress along the n vector of this green plane. Now, as I said, this green plane is parallel to YZ plane, and as a result, its normal vector, its n vector, is in the direction of the x-axis. So I'm going to show the stress with sigma x. This is the same as sigma n from the previous page. Now, sigma t in the previous page was along or tangential to the surface, right? We can break that into a y and z component here. I will have one shear stress component in this direction and one shear stress component in this direction. I'm going to label the top shear stress tau x y and name the bottom shear stress tau x z. So the naming convention is that the first subscript shows the axis that is normal to that plane. In this example, x-axis is the normal vector of this green plane. So x comes in as the first subscript. The second subscript is the direction of the shear stress. For the top one, as you can see, the red arrow is in the direction of the y-axis, so this becomes tau xy. For the bottom one, it's parallel to the z-axis, so it becomes tau xz. So this is a naming convention that we are going to use for different shear stresses on a single particle or a single element. Now, if you want to put a equation for these shear stresses, you can say, okay, sigma x is the fx over the area. Let's say the area of this green plane is just A. Tau xy is fy over A, and tau xz is fz over A. Fx, Fy, and Fz are the three components of the surface force F acting on this particle. I'm going to draw it here just so that we know what we're talking about. Let's say this is F, and so it will have an Fx component here, and then Fy component like this, and an Fz component like this. Okay, now we can talk about viscosity. At the beginning of this video, when I was talking about the difference between a solid and a fluid, I said that under a certain shear stress value, solid goes through a deformation while the fluid will continue to deform, right? Now for a solid, we know that deformation, that strain causes the stress. So for example, for the solid, I know that the stress is related to the strain through the Young modulus. Here, sigma is the stress, epsilon is the strain, and capital letter E is the Young modulus, right? For the fluid, however, this deformation is continuous. So I don't have a value for the deformation in the form of strain to relate the shear stress to the strain. So we are going to relate the stress to the rate of deformation. Okay, so let's take a look. So for the fluid, let's say I have this fluid element and I am going to apply shear stress on top of it. Shear stress tau. Okay, now this fluid element that I have is very small. Its side is dy. So this fluid element over a time frame of dt has gone through this deformation, this red deformation. Now, I know that the deformation is continuous, and as a result, I had to constrain it by choosing a finite dt. Now, over the time dt, this fluid element has deformed from the purple rectangle to the red shape. Now, I'm going to say that, okay, the angle that is created here is alpha, and the rate of deformation of this fluid element is actually related. Rate of deformation is actually the alpha over dt. Now, remember, we want to relate the shear stress to the rate of deformation. I want to find a relation between tau, shear stress, and rate of deformation, d alpha over dt. So my goal is this. My goal is to relate tau d alpha over dt. So let's see what we can do. Now, this is the same element. Now, point A, which was here at t equal to 0, has moved here to A prime after dt, right? I want to know how much A has displaced. So I have two ways of finding that. Way number one is using alpha and dy. Let's say this displacement is ds. So ds is d alpha dy, right? If the motion is small, if dt is sufficiently small, then this entire deformation is small enough that we can assume that AA prime has moved on an arc where the center is here. I'm going to call it O. And you know that in order to find the length of an arc, you can multiply the angle by the radius. Here, radius is dy and the angle is d alpha. So ds is d alpha times dy. On the other hand, because of this shear stress, the top layer of this element is moving with a velocity du, right? So I can find ds using du. The corner of the element has moved from point A to point A prime with a velocity of du over a time frame of dt. So s is actually du dt. Now I have two equations for ds. I can equate them. This gives me d alpha dy is equal to du dt. Playing with this equation a bit, I get d alpha over dt is du over dy. I knew that tau has a relation with rate of deformation d alpha dt. d alpha over dt is not something that I can really use. It's not good enough for me because it's not a flow property. However, du over dy is, and I found a relation between d alpha over dt with du over dy. So, I use that. Now here, we need to divide fluids into two main categories. Category 1 is called Newtonian fluids. And for Newtonian fluids, tau is linearly proportional to du over dy. For non-Newtonian fluids, the other group, this is not the case. Tau is not linearly proportional to du over dy. So let's first focus on Newtonian fluids. Nearly all of the common fluids that we deal with, like water, oil, air, nitrogen, oxygen, any of these common gases and liquids fall into the Newtonian fluids category. As I said, for the Newtonian fluids, tau, or shear stress, is linearly proportional to du over dy. Now, the coefficient that makes this proportional relation into an equation is called the viscosity. We say tau is viscosity times du over dy. Mu is called viscosity Sometimes we refer to it as absolute viscosity or dynamic viscosity. Its units in SI system of units is Pascal seconds or kilograms per meter second. We also have nu, which is mu viscosity over density, and we refer to it as kinematic viscosity. Units is meters squared over seconds. Now, both absolute or dynamic viscosity and kinematic viscosities are commonly used in fluid mechanics. Mu and nu are properties of the fluid, and generally they are a function of temperature. If the changes in temperature are negligible, then we can assume that during the flow, the viscosity of the fluid remains constant. Now, non-Newtonian fluids are different. Here, we don't have a linear relation between the shear stress and the rate of deformation. Based on how the shear stress behaves with respect to the rate of deformation, we will have different types of non-Newtonian fluids. Now, examples of non-Newtonian fluids are things like toothpaste, blood, paint, nail polish, stuff like that. Now, for a wide range of non-Newtonian fluids, we can use this equation to relate the shear stress to the rate of deformation. Tau is equal to K du or dy to the power of n. Now, this is an empirical equation, meaning that it's been derived using experimental data. However, this is not the form that it's commonly used. We really want to format the equation as close to Newtonian fluids as possible. So we usually write it in this form. K du over dy power of n minus 1 times du dy, and then bundle this two terms together and call it eta, and say, okay, tau is eta du dy. Now, the reason for this is the Newtonian fluids have a relation between the shear stress and the rate of deformation, a linear one. We really want our equation to be as close to that equation as possible. So we write it like this. However, unlike the Newtonian fluids where mu is constant, if temperature changes are negligible, eta here is not a constant. It is a function of rate of deformation. Now, in this equation, eta is called the apparent viscosity. Now, based on how apparent viscosity behaves, we will have two major non-Newtonian fluid groups. Group 1 is where eta is smaller than 1. We call these pseudoplastics. For pseudoplastics, the apparent viscosity decreases with increasing the deformation rate. In other words, these fluids feel thinner with the more deformation rate that you apply to them. A very good example of this pseudoplastics is the nail polish. Other examples are whipped cream, ketchup, and even blood. Now, if apparent viscosity is greater than 1, we call this category dilatant or shear thickening. This means that by increasing the rate of deformation, the apparent viscosity increases. Now, a very common example of a dilatant fluid is the wet sand on the beach. Now, when you are walking on a wet sand on a beach next to the water, if you're walking, meaning that you are applying relatively small values of deformation rate, your feet actually sink in the wet sand, right? However, if you start to run on the beach, because your deformation rate increases because you're pounding your feet on the wet sand, you can instantly feel that the wet sand becomes harder and harder, and you can run on it relatively easily. When you were walking, your feet would sink into the sand. When you're running, it's as if you're running on asphalt. Okay? The reason is that the wet sand is a dilatant fluid, meaning that by increasing the rate of deformation, shear stress increases rapidly. There is another category of non-Newtonian fluids that is a bit different than pseudoplastics and dilatant fluids. It is called the Bingham plastics, and they are a bit different in a sense that uh, they behave like solids under shear stress for a certain duration until the amount of shear stress reaches the yield stress of their solid phase. After that, they collapse into a fluid uh, state and behave like a Newtonian fluid. A very common example of a Bingham plastic is the toothpaste that we use every day. Now, when you put the toothpaste on your brush, let's say this is the brush, you put the toothpaste on your brush, it stays like that, right? It stays like a cylindrical shape on your toothbrush, just like a solid. It doesn't fall like a liquid. Like if you put water on your toothbrush, it will not stand there, it will just flow away. The toothpaste, however, stays there just like a solid. But when you start to move your toothbrush against your teeth, the toothpaste becomes a liquid and starts to behave just like a liquid. The reason for that is the moment you start to move your toothbrush against your teeth, you are actually applying shear stress onto the toothpaste. It can withstand some shear stress, but the amount of pressure that you apply on your teeth is greater than its yield stress, and so it breaks down into a fluid state and just behaves like a fluid. So the equation that we are looking for a Bingham plastic looks like this. Tau, shear stress, is equal to tau y plus mu p du over dy. In this equation, tau is the shear stress, tau y is the yield stress for its solid state, mu p is again apparent viscosity, and du over dy is the rate of deformation. Now, please take note that when the Bingham plastic goes into the fluid state, when the shear stress is greater than the yield stress, the amount of shear stress changes linearly with the rate of deformation. So after you conquer the yield stress of this Bingham plastic, it behaves just like a Newtonian fluid. If I want to show these fluids on the same chart, I have something like this. This axis is tau, the shear stress. This axis is du over dy, the rate of deformation. Now, Newtonian fluids look like this green line, a linear relation. I'm just going to show it with n. So the green line is the Newtonian fluids. The relation between shear stress and the rate of deformation is linear. Bingham plastics follow this orange line. Bingham plastics, where this is tau y, or the yield stress. Now I have pseudoplastic and dilutant fluids to show on this graph as well. Pseudoplastics follow this blue line, where after reaching a certain value for the rate of deformation, if you increase from that amount, the shear stress relatively doesn't change. As you can see, the tangent of this blue line is approaching zero, meaning that for very large rate of deformations, the amount of tau or shear stress is not going to change much. Finally, the dilutant fluids follow the red line, where apparent viscosity increases by the rate of deformation, meaning that at the smaller values of rate of deformation, we are going to experience higher shear stress inside the fluid. Like always, thank you for staying till the end of this video. If this video helped you in any way, I would appreciate it if you could leave a like or a comment and maybe subscribe for future videos. Thanks again and see you in another one.